So thanks for that, Alex. So in this second session, I'm going to focus on two topics. I'm going to begin with a discussion on thresholding. So thresholding is one of the most basic operations that can be performed on a graph. And in the second part of this session, I'm going to focus on network statistics, and I'll present some software and some tools that can be used to perform comparisons on connectomes. So to begin with, thresholding is one of the most basic operations that can be performed on a connectome. It simply involves ordering the connections according to weight. So this might be the streamline count for structural networks, or it could be the functional connectivity for functional brain networks, and then eliminating the weakest connections until we reach a desired connection density. The reasons for thresholding is that thresholding can improve the clarity of connectome visualization. It can eliminate spurious connections, and finally, we'll see in a moment that it can emphasize certain topological properties. So here's a topological view, a toy example of thresholding, where I've defined three types of connections: weak, moderate, and strong, as denoted by the width of the edges. So in the unthresholded graph, in the top left corner, we see all three of those connections are present. But in the first step, the first thresholding step, we eliminate the weakest connections, and we arrive at a connection density of 20%. And then we can do one further step where we eliminate the weak and strong connections, and we arrive at a connection density of 13%. Note that once we keep only the strongest connections, we end up with a fragmented node, a node that's disconnected from the rest of the network. And this can present problems in further graph analysis. And so in a moment, I'll present some methods that can avoid this issue of fragmentation. One of the key concepts to thresholding a graph is the concept of connection density. And this is a really simple concept. It's just the actual number of connections in the network after the network has been thresholded, divided by the total possible number of connections in the network. So I've given a trivial example there at the bottom of the slide, a network that involves 9 nodes. And we know that the total possible number of connections in this network is n, if n denotes the number of nodes, n times n minus 1 divided by 2. And so in this case, we have 9 nodes, and that equates to 36 connections. And the actual number of connections after we've thresholded in this toy network is 16. And therefore, the connection density is 16 on 36, or 44%. So the connection density allows us to quantify the severity of our thresholding. The lower the connection density, the more severe our thresholding operation has been. Now, once we've thresholded our network, an optional step that we can then perform is binarization. This step can be performed if we perhaps don't have very much confidence in the distribution of edge weights, or we want to ignore edge weights. And so what we're left with is either a characterization in which we only are interested in the presence or absence of a connection. So in the connectivity matrix shown in the bottom right there, connections are encoded as either a 0, which is an absence, or a 1, which is the presence of a connection. Now, this is an optional step. It's not necessary to perform binarization. Okay, so let's look at thresholding methods in a little more detail. By far, the most common thresholding methods in connectomics are density and weight-based thresholding. So at the top of the slide there, I've shown a toy network, and the weights, or the numbers assigned to each edge, correspond to the weight. So these could be, for example, streamline counts. With density thresholding, the method that I've shown on the left, we prescribe a desired connection density, and we eliminate connections. We eliminate the weakest connections until we arrive at the prescribed density. And this can be done with the MATLAB. So there's a brain connectivity toolbox which is available in MATLAB, and the function called threshold proportional can perform density thresholding. The other very popular method for thresholding is weight-based thresholding. Now, with weight-based thresholding, rather than prescribing a connection density, we prescribe a desired weight. So we say, for example, any connections that comprise fewer than 3 streamlines are eliminated from the network. And as you see from the network in the bottom right-hand corner, we've eliminated the 2 weak connections, the connections that have a weight of 2 and 1. Now, from the perspective of an individual subject, if we're only studying an individual subject, these 2 methods are effectively the same. So if you prescribe a connection density, I can always give you an equivalent weight-based threshold to achieve that connection density. So there's a one-to-one relationship between weight and connection density. So you might ask, well, what's the point? Why am I telling you about these 2 methods if they're effectively the same? Well, the difference between them comes about when we look at groups of subjects. And here's an example. So this is looking at weight thresholding. Once again, the networks on the left correspond to the unthresholded networks, and the networks on the right are the thresholded ones. And in this case, I've decided to eliminate the moderate and weak connections. Now note, with subject 2, the subject shown in red, overall, there's a greater frequency of weak connections. They're the ones that are shown with the thin lines. Therefore, when we prescribe a weight, we see that there's, in the thresholded networks, there's a difference in connection density, or in other words, there's a difference in the number of edges. So subject 1 comprises 7 connections, whereas subject 2 comprises only 3. And that's because subject 2 overall comprises a greater frequency of weak edges. Now, the problem with this, if we then go on to do further graph analysis or some kind of, or analyse particular network measures, and we compare the network measure between subject 1 and subject 2, any difference in that measure might be simply or might be trivially due to that difference in number of edges. So we know that many network measures are crucially dependent on the number of connections in the network. And so this is a potential confound of weight-based thresholding. So let's look at density thresholding. So you might say, well, maybe we should use density thresholding. And by definition, if we threshold based on connection density, we ensure that we have the same number of connections in both subjects, so we avoid that confound. But what we see now with subject 2 is that we're adding potentially, we need to add weaker connections to the network to make up the numbers, to ensure that we have the same number of connections as subject 1. And these weaker connections that we're adding, these could be potentially spurious. They could be false positive connections, either due to tractography, to errors and limitations in tractography. And so it could be argued now, if we compare subject 1 and subject 2, even though they're matched in terms of number of edges, any difference that we find in a higher order topological measure might be confounded by the addition of these spurious connections. So Martijn van den Heuvel has an outstanding paper on this that was published last year. So if you're interested in more details, take a look at his 2017 paper. So just to contextualise this in a little more detail, here's a schizophrenia example. Now, in patients with schizophrenia, functional connectivity is typically reduced compared to healthy comparison subjects. So if we use weight-based thresholding and we set a weight of 0.2, so that means we eliminate any functional connections with a Pearson correlation that is below 0.2, we see that the patient ends up with a connection density of 53%. That's because the patient overall has a greater proportion of weaker functional connections. In contrast, the healthy control ends up with a connection density of 75%. So we have a strong difference in connection density. Now, in contrast, if we use density thresholding, sure, we ensure now that the connection density we guarantee that the connection density is the same between the 2 groups, but we really need to lower the bar for the patient. So we need to drop the minimum connection weight to 0.31 for the patient to ensure that we match in terms of density. So we need to lower the bar. We need to admit weaker connections into the patient network to allow for this density matching. Now you might ask, how would we choose a connection density threshold? So if we've decided that we're either going to do weight or density-based thresholding, what would we do? Should we choose a connection density of 15%, 20%, or 50%? What I would recommend is that you repeat your analysis for a range of connection densities. So if you're looking at a particular network measure, you could consider a range of densities, evaluate your network measure across the range of densities, and in that way ensure that your analysis is not contingent on one arbitrary choice of network measure. And what we can then do is we can take a summary across a range of measures, and that can be the AUC, the area under the curve, and that provides a single summary score that captures behaviour across a range of network measures. Once again, the crucial point of doing this is that we ensure our analysis is not dependent on one arbitrary choice of connection density. Okay, so thus far, the two methods that I've described for connect time thresholding are by far the most prevalent that you'll find in the literature. I would estimate that 95% of the literature either uses weight or density-based thresholding. I've identified some limitations of these, so now I want to present some alternative methods. One is consensus thresholding. The approach here is that we say we want to keep connections that are consistently found across a group of subjects. So in this example, we say we want to keep connections for which at least two of the three subjects are found to have a strong edge. And so you can see there if you look at subject 2, the threshold of network of subject 2, there's a weak connection present. But the reason why that weak connection is present, if you look at subject 1 and subject 3, that connection is strong. So there's a consensus across subjects which allows that weak connection to be maintained. Another approach is the minimum spanning tree. If you remember, I mentioned that if we threshold our network severely, we can have nodes that disconnect from the network. And this is biologically unrealistic. It can also lead to problems in the computation of some graph measures. The MST guarantees that our network remains connected. So basically the steps that we do is there's a MATLAB function that will find the MST for us, and then we can add additional connections until we arrive at our desired connection density. The methods that I've presented that far are considered global thresholding methods. So we define one connection density or one weight-based threshold, we apply that to the whole network. Alternative methods are referred to as local thresholding, where we are interested in thresholding different neighbourhoods or independently thresholding each neighbourhood of the network. And this can emphasise properties within locales or within a given neighbourhood of the network. And I've given an analogy there of this oriental tiger. So you can see with local thresholding methods, we're better able to resolve, for example, the facial features and the toes of the line. And it's the same for a network. So one popular local thresholding method is the disparity filter. I won't go through the mechanics of that here. If you're interested, you can go through the slide. My slides are available for download. I'll put up the website at the end of the talk. But I just wanted to point out that if you look at the red node, you see that the edge with weight 1 is eliminated in the thresholded network. That's in the bottom right network. However, for the green node, the edge with weight 1 is maintained. So whether or not 1 is considered to be a meaningful connection depends on where it's located, what particular local neighbourhood of the network in which that weight is located. Another one is window-based thresholding. This is rarely used in connectomics, and I won't go through the details of that here. So just to summarise, I've presented global methods for thresholding. The two most popular methods that are used are weight-based and density-based thresholding. I've also introduced consensus thresholding, where we seek to find a consensus across a group of subjects. The MST, the minimum spanning tree, can be used to ensure that our network does not fragment, so there's no disconnected nodes. I've also briefly touched on local methods. In particular, I mentioned the disparity filter and window thresholding. With these methods, we can emphasise or we can highlight particular parts of the network, but properties within a given neighbourhood of a node or a neighbourhood of a connection. Once we've thresholded our network, we can then optionally binarise. So remember, binarising removes any information about weights, so we're only interested in whether a connection is present or absent, so we encode connections with a 1 or a 0. And I've also mentioned that we should consider a range of, so in whatever analyses that we perform or the network measure that we're interested in quantifying, we should evaluate that measure across a range of connection densities to avoid our analysis being dependent on one arbitrary choice of connection density. So now I want to move on to comparing connectomes. So what I want to consider here is that perhaps you've acquired some structural imaging data or functional MRI, you've mapped your connectome, you've thresholded it with either weight or density-based thresholding, and then you want to identify particular connectome features, attributes that differ between a patient or a control group, or that might be modulated by a behavioural measure or some sort of cognitive measure, or alternatively that might be modulated by an intervention. So what particular attributes of the connectome can be studied and can be identified between groups or associated with a behaviour? There's really three scales of comparison. The basic most comparison, which is at the bottom of this hierarchy shown in blue, is a global comparison. This is where we characterise an individual's connectome with one single summary measure. And of course, the statistical comparisons here is pretty straightforward. We can use our usual statistical toolbox. So for example, if we were to characterise the path length in each individual, we could perform a t-statistic to compare between the two groups. I'm going to specifically focus on the upper two levels, the node level comparison and connection level comparison. The advantage of these approaches is that we can actually identify, we can localize effects to specific connections or specific nodes. In contrast with the global approach only tells us there's a difference somewhere in the connectome. It doesn't tell us, it doesn't allow us to localize that difference to a particular node or a particular connection. So a very simple way of performing connection level comparison is with mass univariate hypothesis testing. So what is that? What is mass univariate hypothesis testing? Well, very simply, we choose our statistical model. So this could be a t-test if we're looking at between group differences, an ANOVA, ANCOVA, perhaps a regression or a correlation. And we fit that model, we test that model at each connection in our connectome. And this is done independently for each connection. Now, typically there's thousands or perhaps tens of thousands of connections in the connectome, so this gives rise to a massive multiple comparisons problem. And so after we've run the model, after we've performed our test at each connection, each connection is endowed with a uncorrected p-value, a test statistic, so this could be a t-test or an f-test, as well as potentially an effect size. So the question is, how can we correct for multiple comparisons? So one way to do that is with generic methods, such as the false discovery rate, or perhaps Bonferroni correction, which would perhaps be too severe in this situation. I've given an example of FDR on a toy network in my slides. I won't go through the mechanics of that here. You can take a look at my slides and work through the example if you want to learn more about the false discovery rate correction. But what I would like to say is that generic methods, such as the false discovery rate and Bonferroni, ignore the topological configuration of effects. Now, in brain networks, we very often see that effects in a connectome are seldom confined to a single locus. So as I've shown in the left network there, it's very rare that we see one effect in a connection up here and another effect somewhere else in the network. We're more likely to see that these effects, so for example, between group differences or correlation with a behavioural measure, encompass multiple connections and nodes which form an interconnected subnetwork, as I've shown in the network on the right. Ultimately, these subnetworks are constrained by the anatomical network topology, so the axons and the fibre bundles that interconnect different regions. Now, methods such as the false discovery rate treat these two cases, the unlikely case and the likely case, exactly the same. There's no difference in the way that the false discovery rate performs on the unlikely and the likely case. So what we can do, we can consider alternatives to the FDR to boost our statistical power. We can seek to reject the null hypothesis or to test our effects by looking for subnetworks, by actually specifically looking for effects that form these interconnected networks, these subnetworks. One approach to doing that is with the network-based statistic. This is a very simple approach. So once we've performed statistical testing on each edge, we can then prescribe a threshold. So that could be, for example, a minimum meaningful effect size. It could be a test statistic, or it could be an uncorrected p-value. So for example, we might say we're only interested in effects that exceed a Cohen's d of 0.8. And in that case, we throw away all the connections that have a Cohen's d below 0.8, and we're left with the network that I've shown there, that frontotemporal network that I've shown there on the bottom right of the slide. Then the question becomes, what's the likelihood that this interconnected network has come about as a matter of chance? Is it likely that this is just a random chance that we see a connected network which comprises 5 connections, the network that I've shown, the frontotemporal network that I've shown on the bottom there? Or is there some statistical evidence to say that this is pretty remarkable that we find a subnetwork that comprises 5 edges? So to do that, we can use a process called permutation testing. And permutation testing allows us to ascribe a p-value to any subnetwork that we have found. I won't spend too much time on permutation testing, but in effect what we do is we generate multiple permutations, thousands of permutations, and for each permutation we swap the labels between patients and controls. So we can do this simply by tossing a coin. If the coin lands on heads, we swap the patient's data with the control's data. So it's as if the research assistant perhaps screwed up and he or she labelled the data incorrectly. In contrast, if the coin lands on tails, we leave the data as it is. And once we've done this, once we've permuted our data, once we've scrambled our data as such, we then go through the same steps again. We compute our test statistic, we threshold, and we see what's the size of the largest subnetwork in this permuted data. So you can see here with permutation 1, the largest size is 3, and this would suggest, well, in our we observe 5, so that's pretty remarkable that we only see 3 at permutation 1. Permutation 2, we only see a network of size 1, but once we get to permutation 3, we get a network of size 10, and that would suggest, well, maybe the network that we observed is not particularly remarkable because after 3 permutations, we already see a subnetwork that is of greater size. But we can keep doing this, so we can keep doing this for hundreds of permutations. Here I've shown 10 permutations, and we can see for all of the 10 permutations except for 1, that the size of the largest subnetwork is smaller than the size of the network that we find in our actual data. And this would suggest that a subnetwork of size 5 is particularly unusual. So there's something interesting about finding a subnetwork of that size. And so here I've shown where I've generated thousands of permutations and I've generated an empirical null distribution. So the horizontal axis is the subnetwork size and the vertical axis is the number of permutations. So to compute a p-value, all that we do is we say, what's the proportion of permutations in which we find that the subnetwork size is equal to or exceeds a value of 5. Remember, 5 was the number of connections in our observed frontotemporal network. And so it turns out that it's significant. So we have a p-value of 0.002. Okay, so this approach has been used to test a lot of differences across patient cohorts, as well as to identify effects associated with cognition and behaviour. I've given a few examples of those studies here. Finally, I just wanted to mention that one of the limitations of this approach, and it's a general limitation of mass univariate testing, so when we're testing each edge in our connectome independently, is that we're really boiling down these complex network interactions into isolated elements, into edges and nodes. We're treating the edges and the nodes independently. An approach to, or multivariate inference can overcome that limitation, and the idea of multivariate inference is really to learn or to recognize complex patterns that span multiple network elements. So rather than treating each edge and each node independently, we try to look for patterns across sets of nodes and across sets of edges in our connectome. I've listed a few methods to do that. There's CCA and PLS, which are related approaches. There's sparse regression approaches. MDMR, multivariate distance matrix regression, and of course, as many of you would have probably heard about, there's machine learning approaches such as support vector machines. I'm not going to go into any of the details of these approaches here. If you're interested in software, I've listed some software here for performing network inference on connectomes. I must say that this is not an exhaustive list, and if you go onto NITRC, there's a wide variety of software that has been developed for performing inference. In a moment, I'll present a brief demonstration of the NBS. So in concluding, I'd just like to mention that my slides are available for download, so you can go onto that website and download the slides. If you're interested in further information about comparing connectomes and thresholding, take a look at Chapter 11 in our book. This is with Alex Fornito and Ed Bullmore. And finally, I'd just like to mention that we're advertising a research fellow position, a postdoc position in network neuroscience. It's a 3-year position in Melbourne. I'm very happy to chat with you about that if you have any questions, or you can take a look at the website. So just to round out this session, I wanted to give you a very brief demonstration, I think I have 5 minutes left, of the NBS software that I mentioned in the latter part of my talk. So the NBS can be downloaded from the NITRC. It's a MATLAB package. To open up the package, if you just type NBS, it will open up the NBS GUI. And the GUI comprises 3 main blocks. There's the statistical model. Well, first of all, I should say, when you download the software, it comes with a schizophrenia example. So as soon as you open the software for the first time, it loads up the various inputs with the data from the schizophrenia example that's provided as part of the software. And this schizophrenia example are functional connectivity matrices, and the aim is to identify functional connections that differ between patients and controls. So the first block is we specify our particular statistical model, and this is done by specifying our model with a general linear model. I'll give you an example of a design matrix in a moment. This is a very flexible framework for specifying models, so we can specify t-test, f-test, ANCOVA, ANOVA, and so on. It's the same type of approach that you would use, for example, in FSL randomize or SPM. This is the threshold here, so this is a test statistic threshold. This is where we specify which connections we want to eliminate. So for example, if the connections are below a certain threshold, below an effect size, we can eliminate those connections a priori. The second set of inputs is our data. So the input to the NBS are the connectivity matrices for each subject. So it's sufficient to list the connectivity matrix for only one subject, and the software will find the remaining subjects. In this case, the connectivity matrices are provided as text files. You can also provide them as MATLAB files. And optionally, you can also provide the node coordinates and the node labels for your brain parcellation. This is to enable visualization. So to set the software running, all that we do is we hit the button, and this will initialize permutation testing. So in this case, we're going to generate 5,000 permutations, and we're testing the null hypothesis of equality in connectivity between the patients and the controls. And you can see the permutations being generated here. We've found in our actual data a network comprising 40 edges. And here is the network that's found to be significantly different. So we find here a p-value, and this is a visualization of that connectome. This can then be imported into packages such as BrainNet Viewer to come up with 3D visualizations. Now, you might be interested in testing, what about if we lower the threshold? So for example, we can drop the threshold and be more lenient. So we can put a threshold of, say, perhaps 2.5. and run that again. And what we'll find now, given that we've lowered the bar, we should find that a greater number of connections have been included in the network. Now, selecting the threshold can be a little bit difficult. It's never clear exactly how that threshold should be chosen. And there are approaches that have recently been developed, threshold-free approaches for the NBS, and we hope to include these in the software in the next few months. So as you see here, we've lowered the bar and the network becomes much more densely populated and probably harder to interpret. Now you might be also interested in, I'll put that back to what it was. So at the moment, this contrast vector is testing for lower connectivity in the patient group. If we want to test the alternative hypothesis, in particular increased connectivity, we can just reverse this contrast around, and this will run again, and this will now test for an increase in functional connectivity in the patient group. And I won't wait for this to run, but it will turn out that there is no increase. So finally, I just want to give you an example of how the design matrix would look. So if you actually open up when you download the package, this is what you'll find in the folder. Open up the schizophrenia example. It gives you an example design matrix for a t-test. Perhaps I'll open that in a different in a different program. And so the design matrix, in a nutshell, every row corresponds to a subject, and each column corresponds to a subject mean. The biggest question that's so there's a forum on NITRC, a help forum. The biggest question is how to formulate a design matrix for particular statistical designs. Now in my slides, if you look at the end of my slides, I've provided as an appendix several example design matrices for repeated measures design, for group by time interactions and so on. So if you're interested in a particular statistical design, take a look at the appendix of my slides, or alternatively go on to the forum. There's a whole range of examples there. Most people get stuck in terms of how to formulate a particular statistical design. So I'm going to stop there. I'm happy to, I think we have a few minutes for questions, so I'm very happy to take any questions. Are there any online questions? No? Are there any questions in real time? Yep. So, sorry, do you want to just perhaps go towards the microphone?
So thanks very much for your presentation. I have a question that are there some specific criterion for choosing the threshold in NBS?
Yeah, that's a good question. So what I would generally suggest, you may have a minimum meaningful effect size. So you might say that I'm only interested in effect sizes that exceed a Cohen's d of perhaps 0.6 or 0.8, and then you can convert your Cohen's d to a test statistic and use that. Alternatively, there's approaches that have been developed, threshold-free approaches, that don't require you to specify a threshold. So in the coming months, or at least this year, we hope to incorporate these threshold-free approaches into the software, and this would then mean that you don't need to specify a threshold a priori. But for now, I would suggest that you choose a threshold based on either a minimum meaningful effect size, or perhaps you could choose an uncorrected p-value of, say, 0.001. I mean, this is the same problem that comes about in cluster-based statistics. So with cluster-based statistics, we need to specify an initial cluster-forming threshold, and there's a lot of debate about how that threshold should be, that uncorrected p-value should be chosen.
Okay, so for now, we just try and error for choosing the threshold.
Sorry, try
and error.
Trial and error. Yeah, I mean that's I guess one option that you could
thanks.
choose.
Thanks.
Yep.
Thanks for your talk. It's very interesting to know the thresholding varieties. At each point or the combined point, we can use thresholding. But how do you deal with the dependency of connections according to time? Dependency of connections,
yep.
Network connections according to time.
So you're talking about dynamic connectivity,
yes.
where we're mapping?
Yeah.
Yeah, so I haven't considered the dynamics of connectivity, and I guess if you're thresholding multiple networks where each of those networks corresponds to a temporal a window, for example, a sliding window, a naive approach would just be to apply the same threshold to each of the windows. But then you might find in particular windows where connectivity, so we know that connectivity varies with time. In a particular window, you might have overall weaker connectivity. And so if you apply that same threshold, then you might end up with a very sparse network at that particular time point. So some care might be needed when doing that. I guess thresholding in dynamic networks hasn't been considered extensively. It's still a topic that needs to be addressed.
Thank you.
I might stop there. I mean, I think we'll have time in the break. In the interest of time, I think we're already a little bit over. So I'd next like to welcome